This is a stochastic processes, Module 7, Brownian motion and its applications. Lecture 4, Ito calculuses, Ito integrals. In the last 3 lectures, we have discussed the definition and properties of Brownian motion in the first lecture. In the second lecture, we have discussed geometric Brownian motion and the other process derived from the Brownian motion and their properties also. In the third lecture, we have discussed stochastic differential equations. In this lecture, we are going to discuss Ito integrals. First, we are going to start with the definition of Ito integral. When we say the stochastic process is Ito integrable, then we are going to discuss what is Ito process. Then followed by these definitions, we are going to discuss few examples. Followed by the examples, we are going to discuss the properties of Ito integrals. So with that, this lecture will be completed. This is the definition of Ito integral. Let xt be a stochastic process which is adapted to the natural filtration f of t of linear process Wt. That is xt be a ft measurable. Define it, I of t, that is nothing but integration between the limit 0 to t x of u, integration with respect to wu, where t lies between 0 to capital T, where t is a positive constant. I of t, a stochastic integral with respect to a Vernier process. The above integral is called the Ito integral. A detailed interpretation and the motivation of this can be found in the reference books. So the Ito integral I of t is defined in the form of integration 0 to t, and the integrand with respect to the integral with respect to the Vernier process W of t. The Vernier process already discussed. The Vernier process or Brownian motion is discussed in lecture 1. You can find in lecture 1 what are all the properties of Vernier process and so on. So the Vernier process Wt is starting with the standard one W0 is equal to 0, and it has increments are stationary as well as independent, and the increments are normally distributed with the mean 0 for the standard Vernier process, and the variance is a increment, the difference. For s is less than t, it is the variance is t minus s. So here we have a stochastic process xt, which is defined between the interval 0 to capital T. The same stochastic process is adapted to the natural filtration f of t. Already we know that the Vernier process is adapted to the Wt, and here xt is also adapted to the Wt. That means for fixed t, xt is a ft measurable. That means the sigma field generated by the xt for fixed t will be contained in f of t. That means the information accumulated at time t, that is sufficient to find out the value of x of t for fixed t. So the xt is ft measurable for all t between the interval 0 to capital T. Then we can define this integral will be, call it as a Ito integral. So the xt has to be ft measurable, and ft is a natural filtration for the Vernier process Wt, then for all values of t between the interval 0 to capital T, I of t is called the stochastic integral, because this is not the usual integral, this is a stochastic integral with respect to the very near process Wt. This is a definition of Ito integral. Now we are going to discuss the Ito process. Let Wt be the Brownian motion and Ft be the associated natural filtration. A Ito process is a stochastic process. Xt is of the form xt is equal to x of 0 plus 0 to t integration delta u d of wu plus integration 0 to t theta u du. So here we have two types of integration. The one type is the usual Riemann integration. The other one is the Ito integral, where x of 0 is a non-random and delta of u as well as theta of u are adopted process, and the delta of u is a mean square integral. If this condition is satisfied, then we can say this xt is going to be a Ito process. For all t, if you are able to write xt's of the form the one Ito integral and the Riemann integral, and both the integrands are adopted process, that means x of u is fu measurable as well as the theta of u is fu measurable, as well as the delta u is a mean square integral. That means the integration 0 to t expectation of a delta square u du is a finite value. Then we say it is mean square integral. If these three conditions are satisfied by the x naught, delta u, theta u and another, we can say the xt is going to be a Ito process. Once it is a Ito process, you can write down in the differential form, that is a stochastic differential equation, because we have d of w u. In the differential form, it will be, because delta t is equal, xt is equal to x of 0 plus integration, therefore in a stochastic differential form it is a dxt is equal to delta t times dwt plus theta t times dtt. So this is the stochastic differential form of Ito process. It means whenever delta t as well as theta t both are adopted process and x of 0 is non-random as well as delta t is mean square integrable, then the stochastic process written in the stochastic differential form dxt is equal to delta t dwt plus theta t dt will be called it as a Ito process. So the Ito process is nothing but a stochastic process, is of this form as well as satisfying these conditions. The way you write the stochastic differential equation, dxt is equal to delta t times dwt plus theta t times dt. Therefore, if you see the sample path, it is going to be the continuous function. Therefore, all the stochastic process with no jumps are actually a Ito process. Whenever you see the Ito process, you won't find the jumps. A jump Ito process is nothing but a Ito process in which the moments are discrete rather than continuous. So all the stochastic process with no jumps are actually a Ito process, because it has the term of dt as well as a dwt terms for the increment of dxt for all t. Ito integrals as well as the Brownian motion are the examples of Ito process. The way the previously written I of t as well as the Brownian motion, both are called the Ito processes. Now we are going to discuss the Ito integral. If xt and wt are not stochastic process but rather deterministic functions, then the situation is different. Assuming f of s, that means we discussed in a deterministic situation, we return integration is 0 to t g of s d f of s, where f of s is a differential function and g of s is the smooth function. Since it is a differential function, you can write d of f of s as the f dash of s ds, which is nothing but the Riemann integral. Whenever xt and wt are non-stochastic processes, rather deterministic functions, then you can write down this integration as a g of s df of s, that is nothing but the Riemann integrals. But in our situation, the f of s is not a differential. We can still define the integral. Remember that the wt, which is a nowhere differentiable, as well as a unbounded variation. So here we are going to discuss when f of s is a non-differentiable as well as when f is bounded variation, then still the integral is well defined. Further, if the function g of s is extremely fluctuating at different points in time, the limits may still diverge. When f of s is bounded variation, we can prove that the integral is well defined. Further, if the function g of s is extremely fluctuating at different points in time, the limit may still diverge as s tends to infinity. Since f of s is bounded variation, one can prove that the limit exists as long as g of s is not varying too much, and it is given by the integration 0 to t g of s df of s is nothing but limit n tends to infinity, summation of I is equal to 0 to n minus 1 g of si integration with the difference f of s plus f of si plus 1 minus f of si. That means since the integration is with respect to d of f of s, so you can find the difference f of s plus I minus f of si, then multiplied with the g of si, and that means you are partitioning the interval 0 to t into n parts. Then as n tends to infinity, that summation limit n tends to infinity will be the integration. Since f of s is bounded variation, you can prove that the limit exists. Remember that in the integral 1, that is this is integration, the Ito integral I of t x of u is a random variable for fixed u, w is a random variable for fixed u, and wu is a nowhere differentiable as well as a unbounded variation. Now we have discussed what is the situation if f of s is a bounded variation. The integration with respect to f of s, where f of s is bounded variation. Whereas our Ito integral xt and wt are stochastic processes, as well as wt is unbounded variation and nowhere differential. So that's the difference between the Riemann integral and the integral which we have discussing now, that is Ito integral. The integrand is x of t. The integration with respect to wt, where wt is a unbounded variation as well as nowhere differential. Whereas the Riemann integral which we have discussed, the f of s is differentiable, as well as later we discuss f of s is a bounded variation. Whereas the Ito integral, wt is a unbounded variation as well as wt is nowhere differential. Hence, it is different from the Riemann integral. So in the Riemann integral, the integration with respect to the function which is a bounded variation and it is differentiable, whereas here in the Ito integral it is unbounded variation as well as nowhere differentiable. Now we can rewrite the Ito integral 1 in the above form, in the following form. I of t, that is nothing but the way we have written in the above form Riemann integral, integration with respect to integration of 0 to t g of s with respect to f of s is limit n tends to infinity. The same way you can write I of t is limit n tends to infinity summation I is equal to 0 to n minus 1, because the integration is the integration 0 to t x of u d of w, therefore it is x of si and the w difference, that is w of si plus 1 minus w si. The way we have written the Riemann integral, in the same way we are writing the Ito integral where xt is a adapted process and wt is a stochastic, wt is a Vernier process or Brownian motion, and xt is adapted to the f of t, and the Ito integral I of t can be written as a limit n tends to infinity, the summation form.